What if what we call empty space isn't empty at all? I mean, what if that seemingly passive void is actually uh, teeming with hidden energy, constantly shifting, and maybe holds one of the most profound puzzles in modern physics? Today, we're taking a deep dive into the quantum vacuum, its mind-bending fluctuations, and this colossal enigma known as the cosmological constant problem.
Yeah, exactly. And this deep dive, it's really designed to give you a shortcut to getting informed on a topic that spans the incredibly small and, well, the incredibly large. We'll be pulling insights from foundational science like quantum field theory and the Higgs field, maybe venturing into more speculative realms like Jacobo Grinberg's lattice theory and even string theory. And then we'll bring it all back to cutting-edge research on quantum fluctuations and their measurable effects. Our mission really is to uncover the dynamic nature of space and the profound implications this has for how we understand reality. Give you those surprising facts and just enough maybe interesting twists to keep you hooked.
Okay, let's really dig into this then. For centuries, classical physics pretty much imagined empty space as pure nothingness, right? Just a passive stage where particles and forces did their thing. But our sources completely upend that idea. So how does modern physics fundamentally redefine empty space?
Well, it's quite the revolution, actually. Quantum field theory, or QFT, it doesn't see particles as these discrete little billiard balls. Instead, it describes all fundamental particles, electrons, quarks, everything as tiny, localized excitations or disturbances within underlying quantum fields. And these fields permeate every single point of space. So even when we talk about empty space, these fields are still humming with activity, continuously interacting and subtly shaping reality at its deepest level. It's really far from a passive void.
Right, right. And this concept got incredibly tangible with the discovery of the Higgs field, didn't it? That wasn't just some abstract idea. Its confirmation changed how we think about something as fundamental as mass.
Absolutely. The Higgs field is a universal scalar field, meaning it exists everywhere, throughout the entire cosmos. Its omnipresence is critical. It's what gives fundamental particles their mass, but not as like an intrinsic property of the particle itself, but through their interaction with this pervasive field. You can kind of think of it like walking through thick syrup. Some particles interact more, get stuck more, and gain mass, while others, like photons, just glide right through. This discovery really confirmed that the most fundamental layer of reality isn't a void, but an interactive, active field constantly influencing everything.
So, okay, if space isn't truly empty, it must be doing something. Our sources mention quantum fluctuations. What exactly are these invisible stirrings and what real-world effects do they actually have?
Right. So quantum fluctuations are these spontaneous, fleeting appearances and disappearances of particles and energy at the subatomic level, even within a vacuum. They're like tiny, temporary ripples in those quantum fields we talked about. One of their measurable impacts is something called the Lamb shift. It's a minuscule but very precise shift in the energy levels of atoms, like hydrogen. These electric field fluctuations subtly nudge the electron, proving the vacuum isn't just sitting there idly. They can also literally give charged particles a sort of kick, increasing their probability of quantum tunneling through barriers they otherwise couldn't pass.
That's amazing, tiny jitters having a real measurable effect. Our notes also highlight the Casimir effect. How does that fit into this picture of an active vacuum?
The Casimir effect. Yeah, that's another classic, tangible demonstration of vacuum fluctuations at work. Imagine you have two uncharged, perfectly parallel metal plates, and you place them incredibly close together in a vacuum. What you find is an attractive force pulling them together. It's small, but it's there. This force is interpreted as being due to a modification of the quantum vacuum fluctuations in the space between the plates, compared to the space outside them. It's almost like the vacuum pressure is pushing them together, proving empty space has real physical properties.
But hang on, these aren't just lab curiosities, right, confined to tiny experiments. Our sources hint that these cosmic jitters might have actually shaped the structure of the entire universe. How does that work?
Yeah, this is where it gets really mind-boggling. A remarkable prediction of inflationary cosmology. The idea that the early universe expanded incredibly fast is that the large-scale structure we see today, things like galaxies and clusters of galaxies, actually originated from the quantum fluctuations of a special energy field, the inflaton field, in that primordial, rapidly expanding universe. These tiny quantum-born density variations were stretched across the vastness of space by that inflation, becoming the seeds for basically everything we observe. So the whole cosmos might have its roots in this quantum fizz.
Wow. And what's fascinating here, too, is how our very act of observation or measurement can influence what we detect from these fluctuations. Can you explain that a bit?
Right. It depends crucially on how you look at them, so to speak. Imagine these quantum fluctuations like tiny waves. For simple things, linear operators like the electric field, they tend to be small and behave predictably, mathematically speaking, following a Gaussian distribution like gentle ripples. But if you're measuring something more complex, like the energy density, which is a quadratic operator, the probability distribution can behave differently. It can have this slowly decreasing tail. What that means is there's a surprising sort of enhanced probability of large, intense bursts of energy popping up from seemingly nowhere, which becomes really critical when you think about how they might affect gravity.
Okay, so then nothing of space is buzzing. You can have big bursts of energy, and it can even theoretically dip into negative energy. That sounds completely wild. What does this mean for energy in empty space? Can it really be negative?
Well, this does raise an important question. And yes, in quantum field theory, the expectation value of energy density can indeed be negative in some regions. Now, this isn't science fiction. It's constrained by rules called quantum inequalities, which limit how negative the energy can be and for how long it can last. For example, in some simplified spacetime models, calculations suggest you could theoretically measure negative energy density up to, say, 84% of the time, even if the overall average value is zero. It's incredibly counterintuitive from our everyday perspective, but it's mathematically possible within the framework, challenging our usual ideas about energy.
The idea of negative energy is already pushing boundaries, but our sources then take us even further into some really speculative territory about the nature of reality itself. Can you tell us about Jacobo Grinberg's lattice theory and how something like string theory might connect?
Sure, if we connect this to the bigger picture, yeah, Grinberg proposed this idea of a non-local lattice of consciousness, basically a pre-spatial framework that, he argued, actually generates reality. In this view, consciousness isn't just something the brain does, but it's primary, actively shaping the space-time we perceive. Then you have string theory, which is, a major contender for a theory of everything. It suggests fundamental particles aren't points, but tiny one-dimensional strings vibrating in higher unseen dimensions. Our reality, in that picture, would just be a kind of slice or projection of this vast multidimensional structure.
So these seem pretty different, but are they just random ideas? Is there some common ground between them, maybe bridging the scientific and the speculative that gives us a fresh perspective?
Well, that's the interesting part. Both theories, despite their huge differences in approach and rigor, they both imply a fundamental layer beneath what we see as matter and observable physics. This underlying layer seems to be defined more by informational principles or vibrational patterns, rather than just mass or charge like we usually think about. It kind of points towards a structured, maybe even encoded reality that might pre-exist physical manifestation, operating more like a complex self-modulating algorithm than a simple clockwork universe. It's definitely a speculative bridge connecting hard science with some pretty deep metaphysical questions about what reality fundamentally is.
That's a fascinating leap indeed. Now, speaking of fundamental questions, this whole discussion seems to lead us directly to its arguably the largest discrepancy between theory and observation in all of physics, the cosmological constant problem. What exactly is it, and why is it such a monumental headache?
Right, the cosmological constant, usually written as the Greek letter lambda. It was actually introduced way back by Einstein in 1917, then he famously called it his biggest blunder. Only for it to make a huge comeback in the late 1990s when supernova observations suggested the expansion of the universe is accelerating, implying lambda is small, but definitely not zero. The problem is this. In quantum field theories, that vacuum we've been talking about, it isn't empty. It's filled with those zero-point fluctuations, the quantum jitters. And theoretically, these fluctuations should give rise to an absolutely enormous amount of vacuum energy density. But our observational bound for this energy, based on how the universe is actually expanding, is incredibly, incredibly tiny. We're talking less than 1029 grams per cubic centimeter. Just minuscule.
Okay, minuscule observed.
Okay.
And the theoretical predictions, that's where the real clash happens, right?
Yeah.
What's the scale of this difference?
Precisely. This is where the headache becomes a migraine. Theoretical estimates for the vacuum energy density coming straight out of QFT, just considering standard stuff like quantum electrodynamics, QED, the Higgs field, quantum chromodynamics, UCD. These estimates exceed that tiny observational bound by at least 40 orders of magnitude. That's a 1 followed by 40 zeros. And if you consider the Planck energy scale, which is where we think quantum gravity kicks in, that discrepancy potentially balloons to over 120 orders of magnitude. It's hard to even grasp. Imagine predicting a grain of sand should weigh more than the entire galaxy, and you're getting close to the scale of the mismatch. It's the worst prediction in the history of physics, arguably.
That is just staggering. How did this problem even get recognized in its quantum form? It wasn't always seen this way, right? It went from Einstein's blunder to this modern crisis.
Yeah, it has a rich quantum history. Some early physicists like Pauli and Nernst had musings about zero-point energy. Lemaitre, back in 1934, was probably the first to explicitly connect vacuum energy to Einstein's cosmological constant. But it was really Zeldovich in the late 1960s who hammered home the point, explicitly highlighting the radical discrepancy between the QFT vacuum energy estimates and the cosmological observations. Then things like the development of spontaneous symmetry breaking in particle physics, the Higgs mechanism is a key example, and the rise of inflationary cosmology in the early 1980s, they really cemented the problem. These theories suggested that vacuum energy wasn't constant, that it changed dramatically in the early universe, driving cosmic expansion. This made the current tiny value even more puzzling. And yeah, even string theory really struggles with this one.
So, okay, what does this all mean for how we understand the universe? If the vacuum theoretically has all this immense energy, why on Earth don't we see its gravitational effects? Why isn't space-time completely warped?
That's the absolute core question. Is this theoretically predicted vacuum energy physically real in a way that actually generates gravity? Conventionally, the assumption is, well, yes, it should. All energy gravitates according to general relativity. The heart of the problem really lies in trying to properly connect the microscopic quantum predictions of vacuum energy to the macroscopic classical gravitational effects described by Einstein's theory, especially when space-time itself is curved or expanding. It's like trying to mesh two fundamentally different descriptions of reality.
And merging general relativity and quantum field theory is notoriously difficult, especially here.
Oh, incredibly difficult. When you try to actually calculate the vacuum's energy in a dynamically changing space-time like our expanding universe, the math just blows up. You run into these huge unmanageable infinities, which is usually a sign that your theories are breaking down or missing something fundamental. Conceptually, even the idea of a perfect vacuum state, a state with absolutely no particles, becomes kind of ambiguous in a general curved or expanding space-time. Why? Because gravity itself can, in theory, create particles from the vacuum. We try to bridge this using something called the semi-classical Einstein equation, which basically plugs the average quantum energy into Einstein's classical equations. But it's not rigorously derived, hasn't been experimentally tested in this context, and it leads to this tricky back reaction problem. Space-time affects the quantum fields, which in turn affect space-time. It's a complicated loop.
But wait, you said the problem still exists despite all these complications. How can we even formulate it if it's so technically challenging?
Yeah, it persists because, fortunately for doing calculations locally, like here in our solar system, space-time is very weakly curved. It's a very good approximation to the flat space-time of special relativity. And cosmologically, on the largest scales, the universe is pretty close to flat and expanding relatively slowly now. These conditions allow us to define a reasonable approximate vacuum state. So the fundamental prediction from QFT of this enormous vacuum energy, which seems to have no discernible gravitational effect astrophysically, remains a profound and undeniable challenge. The approximations are good enough to show the problem is real.
And this idea that the observed near-zero value of the cosmological constant might actually be telling us something fundamental about whether vacuum energy is even real in a gravitational sense, that's a really provocative thought.
It is, and what's fascinating here is a subtle but important argument. You see, effects like the Casimir effect or the Lamb shift, which we discussed. Yes, they can be interpreted as evidence for real vacuum energy, but they always involve material systems, plates, atoms. So it's a little ambiguous. Are we measuring a property of the vacuum itself or a property of how the vacuum interacts with that specific material system? However, observing the cosmological constants, say, through the accelerating expansion of the universe or even precision measurements in the solar system is a purely classical measurement of gravity. It doesn't involve quantum test bodies in the same way. So the argument goes, if the observed tiny lambda is genuinely due to quantum vacuum energy, then the classical measurement itself couldn't somehow be canceling it out or causing it to be small. This leads to a pretty radical speculation. Perhaps the observation of lambda being almost zero is telling us that maybe there isn't any real gravitating vacuum energy associated with empty space and QFT after all. Or at least that our current understanding, our current QFT formalism is fundamentally incomplete when it comes to gravity.
Wow. Oh, okay, so what does this all mean then? How are physicists actually trying to solve this this deepest of mysteries, this staggering disconnect. What are the proposed solutions?
Well, there are many proposed avenues, but it's fair to say there's absolutely no consensus. People are trying lots of things. Some suggest modifying general relativity itself. Maybe the cosmological constant isn't constant, perhaps it changes over time. These are often called quintessence models, where dark energy is some kind of dynamic field rather than just a fixed vacuum energy. Others look toward quantum gravity theories, things like quantum cosmology, speculating about baby universes, or maybe wormholes that could somehow interact in a way that statistically favors lambda being very close to zero in our universe. Supersymmetry, or Theories Y, was a big hope for a while. It postulates a symmetry between fundamental particles, predicting superpartners for each known particle. In perfect Theories Y, vacuum energy contributions would cancel out exactly. The problem is, we know supersymmetry must be broken in nature. We haven't found any superpartners, so the cancellation wouldn't be exact, leaving a residual energy that's still usually way too big. And string theory, probably our most developed framework trying to unify GR and QFT, also faces this as a major, major hurdle. It often predicts a vast landscape of possible universes, each with different vacuum energies, which leads into other debates.
And then there's the philosophical angle, too, suggesting maybe it's not even a problem in the way we're thinking about it.
Exactly. This raises the important question. Is it maybe a pseudo-problem? Some argue that the cosmological constant might just be a fundamental constant of nature, like the speed of light or Planck's constant, something we just measure, not something we should be able to derive from particle physics. Or perhaps our understanding of how general relativity and quantum field theory actually connect is so inadequate that we can't even pose the problem correctly yet. Others invoke what are called anthropic considerations. This basically suggests we live in one universe within a potentially vast multiverse. In most of these other universes, the cosmological constant might be huge, either positive or negative. But in those universes, structure like galaxies couldn't form, so life as we know it couldn't evolve. We therefore find ourselves in one of the rare universes where lambda is just right, small enough to allow stars, galaxies, and ultimately us to exist.
It really sounds like the very definition of the problem hinges on some incredibly deep assumptions about what's fundamentally real and how our best theories of physics actually link up. It's almost like we're debating the rules of the game itself.
Indeed. The whole question of the problem's naturalness is fiercely debated. Is it like the old problem of ether drift, which turned out to be based on a misunderstanding of reality? There is no ether. Or is it more like Maxwell's unification of electricity and magnetism, which pointed towards deeper, undiscovered principles? The core conviction driving the crisis is that quantum vacuum energy, as predicted by QFT, is physically real, and that it must generate gravity according to GR, despite having no direct experimental proof of that specific link at the quantum level. The fact that lambda is observed to be so incredibly small is, in a sense, the most direct experiment we have on the vacuum's gravitational properties. And it forces us to ask, if this tiny value is truly quantum in origin, why doesn't the huge theoretical value show up gravitationally? It would honestly be an overwhelming surprise if it turned out that real vacuum energy did not gravitate. But the current observations, the sheer scale of the discrepancy, they force us to continuously reevaluate these absolutely fundamental assumptions.
So we started just by pondering seemingly empty space, and we've ended up grappling with the very nature of reality, maybe consciousness, and certainly the biggest unsolved puzzles in fundamental physics. This deep dive has definitely shown us that the nothing of space is far, far more complex, active, and consequential than we could ever have imagined.
Absolutely. This whole journey, from these fluctuating quantum fields all the way to the cosmological constant, it really highlights that our understanding of the universe is still very much evolving. It's being driven by observation, yes, but also by this incredible, almost unbearable tension between our most successful theories. It really compels you, the listener, to consider, if the vacuum truly holds such immense hidden potential, what other unseen dynamics might be shaping the reality we perceive every single moment, just waiting for us to figure them out?